Okay, now coming back to now the heat transfer of the motor, I have explained you, right? How heat transfer takes place in a motor. Okay, I showed you one of the two papers. One is by GE and one is by Eaton. Basically, when a heat is generated in the stator winding and rotor winding, the heat will be stored by basically our core, stator and rotor core. See, our windings also store heat depending on the copper mass, and our core also stores heat depending on the iron mass. Then the heat is finally dissipated. Okay, that heat generated is based on the I square R loss and also your eddy current magnetic losses. So add both of them, that will be equal to the heat stored plus heat dissipated. You solve that equation, then you basically get all the curves. Okay. Now, if motor starting and running and motor stalling. See, when the motor stall, what will happen is the cooling will not take place, right? Because the motor is not rotating, air is not circulating. Okay. So the temperature rise also will increase that time. So all those things will be taken into account when you plot those curves, right? How many of you have access to standard IEEE? How many of you have gone through the standard IEEE motor standard?
No, sir, I am not good.
Okay.
Not gone through it, so.
Okay, if you have access, please go through this standard, nice standard. And this standard gives you a lot of information. Please go through this, okay? Then coming to one important thing you have to remember this one, the life of insulation. See, motor life is life of insulation. If the motor temperature increases by 10 degrees, insulation life will reduce by half. Okay. Why I am telling this is, see on this curve, whatever you saw here, no? On this curve, whatever curve you saw here on this curve, basically
At 10 degrees centigrade, sir, 10 degrees centigrade, how long? If it's sustained and it will be, insulation life will be half.
good question, sir. How for how long? I need to check that, sir. Even I am not sure, because normally when we say 10 degrees Celsius, they are not talking about a small duration. That is for sure. Okay, they are talking about sustained in a sustained way. But how long, for that we have to, that we have to. It is not like me telling 2 seconds, 3 seconds, 4 seconds. Okay, it is the time. Again, it depends on those curves, all those things. So exact seconds I can't tell, but I can tell you it is for a longer duration. Okay, longer duration means like maybe more than few 20, 30 seconds, I guess. But it will not be short duration. Short duration, because see, I will show you one. I will draw and show you one thing. Able to see the screen? I have to change the sharing. Hold on. Okay, see. See what happens in a motor, no? Suppose a motor is running and let us say when I start the motor, my temperature may be less. Then the temperature will increase like this and it will be steady state like this. Suppose now all of a sudden I overload the motor, then my temperature will again increase, and after some time it will reach a new steady state. Okay. Now, if I reduce the load, then my motor temperature will come down like this. Okay, and it will be like this. If I again reduce the load, for again it will reduce like this, come down like. So you can see, what you can see here is, you see here, you see here there is a time, right? This is the time. This is, you see here.
Sir, one doubt here, sir.
Yes, sir.
This use
I will just complete this. Hold on, sir. This is the temperature theta. This is the time t. What I want to see. So you see, it is taking certain time for the temperature to come to this point. So, and this depends on, there is a time constant here, tau. Okay. And to get the time constant, that time I showed you one differential equation, no, is the G. If you solve that equation, you will get it. Okay. So basically, see, there is no quick answer for everything, but I can tell you where you will get the answer. The time depends on this curve depends on the differential equation. So how long I can increase the 10 degree, it depends from motor to motor. That is why they have not mentioned exact value. Okay, sir. Sir.
Yes, sir.
Yeah, Mr. Krishna Kumar, please tell me who you have asked some down.
Yes, sir. Actually, this motor is coupled with the pump now, sir.
Pardon?
This normally this motor will be coupled with the pump now for a certain
Motor
flow
coupled with the
condition.
pump. Yes.
And, yeah. So in that condition, how this sudden this overloading will happen, sir?
Okay, sir. I will tell you. See, the motor is basically generating a rotational torque, right? And that rotational torque of the motor is consumed by your pump, right? But there will be some mechanical, like something like, see, normally head flow rate and all is already designed in the beginning. Based on that, they have sized the motor, and they have given lot of that all the efficiency losses and extra overloading, everything they have taken care. They have put a good big motor, but still something can go wrong. Wall may get blocked. Some mechanical something may go wrong. But this rise in this one, no, what I'm telling, see, when the motor, suppose you have a slight change, increase in the motor load. Your question is why the motor get overloaded, load extra? It is because of the pump or the fan. Why pump or fan gets extra loaded? It is because of the process. There are various mechanical reasons for it. Okay. One maybe, like as I told you, the valve may not be fully opened. Like that, lot of reasons are there, not one. You can actually, if you are working in an interdisciplinary company, if you have process guys, particularly the process guys, you just go ask them, process or mechanical guy, under what circumstance the torque of this pump may increase. You just ask them. And I think one of the reason may be our valve also. Valve is not fully opened or something. You can check with them. Okay, sir?
Yeah.
Yeah. Okay, so I will go back to Able to see my screen full big? Able to see my
Yes, sir.
screen? Okay.
Yes, sir.
So basically, I explained you about this thermal curve. Okay, and also explained you about the starting curve. Okay, now let me go to this. Okay, this equation I will go later on. Okay, I will not go to it right now. So how do we plot this equation? See, in the Excel, basically what we do is we will trace this equation, okay? And after tracing this equation, because see, the vendor, if vendor gives, see, in the first place, let me tell you all, we are not going to do Excel based relay coordination in the company. Is that clear for everybody? Is that clear for everybody?
We
Can you
lost your
repeat what
voice.
you just said?
Yeah, can you repeat? We lost your voice.
In your
The
company,
internet froze up, so.
sir, in your company, you will not be using a Excel based relay coordination. Is that clear for everybody?
Yes, sir.
The reason why we are doing this Excel is, see, we want to go to the core and understand the basics. That is the reason we are doing like this. When I use ETAP, how many of you use ETAP?
So I've used it sometimes, so.
Okay.
I used.
Krishna Kumar. And how many of you use this EDSA, Neplan, any simulation software for relay coordination? How many of you have used?
Sir, I have used EAPSM.
Which one?
EAPSM.
PAPS.
EAPSM.
Can you type the name, Mr. Navin Kumar, in the chat box
Yes, sir.
so that others also can see what is the software used? Mr. Loganathan, sir?
Sir, I have not used any
Yes.
simulations.
Okay. This EAPSM is a paid software. Last time also I think you had told me this one. This is a paid software or what?
Yes, sir. It's a paid software.
Okay. So see, for relay coordination, some of the software which I have used is, I will tell you, one is ETAP I have used, ESKM I have used, ETAP, I use ETAP, I use SKM, and I use this Paladin, which was earlier called EDSA. Okay, so we have very good softwares actually, but still the reason why nobody will use this Excel. Okay, remember that. But why we are going to this Excel is we will go deep into the subject. The way the software guy has written, we are understanding that. Okay, that is the reason we are doing this. Okay, let that be very clear. Okay, so now I will go to this motor data sheet. Okay, in the motor data sheet, the motor data sheet is very important for me. Sometimes what is happening, I'm not getting the detailed curve, right? But I want to know the starting current, so I can get from the data sheet. So you see here the start. This is what is the rating, 132 kilowatt motor, ABB motor. I can see my starting current is how much? 7.55 times. Tomorrow I will explain you why, how to determine the starting time. Okay, there is a method. Actually, ABB they have very nicely explained. Previously, there was a material in ABB. I am not able to retrieve that. I don't know. Very nicely, they had explained by integration how to determine the starting time. I could not get that one, but I got other material. Okay. How many of you have worked on drives, variable frequency drive?
Yes, sir.
Gaurav has worked. So please go to our ABB drive section. There are a lot of technical guides there. Okay.
Yes, sir.
Those guides are very nice actually. You can go through those guides. And particularly, so one of you asked about this question, no, today, how the load will increase. If you want to get a good answer for all this, go through that ABB drives technical guides. Don't go to the drive manual or the drive installation guide or those things. The drive section, they're having some technical guide, some 20-30 pages. Okay, you please go through those guides, they're very helpful. Now, why I'm showing you this data sheet, I will explain you some important thing in the data sheet which we should actually make note. One is this starting current is important, starting torque is important, lap rotor torque is important. Okay. Moment of inertia is very important. GD square. I will use all these data to determine the starting time. See, I will actually explain you one of the most important. This one is the. See, this curve is very important. See, this 100% curve. See, this is A is what? A is 100% curve, right? This 100% curve.
Yes.
Yeah, this 100% curve is very important. Okay. This 100% curve is very important. I have to plot this curve before I do the coordination. See, in case of my this one software, my 100%, 80%, 90% curve will get added. But when I'm doing manually, I may not be able to add the 80% curve. But for sure, I will add the 100% curve. Okay. Okay, we can try to add 80% curve also. But for that, I have to determine my starting time at 80% voltage. To determine my starting time at 80% voltage, basically I have to first know what is the starting torque at 80% voltage. How will I get my starting torque at 80% voltage? I go now by one. Mr. Inamul.
Sir,
What is the nominal torque here in the 132 kilowatt motor?
1270
Okay.
Newton meter.
Okay. Anybody please open your Excel and calculator. I need a small request. P is equal to, please write it. Here itself, I think there is a whiteboard. Let me open my Word document. Okay, open your calculator or Excel. I will ask you. Open this one. Okay, let us go. P is equal to 2 pi n t. You know this equation, right? You're there, my dear friends. Are you there? Inamuji,
Sir,
you know this equation, right? P is equal to 2 pi n t.
yes,
P is the power, n is the speed, t is the torque. Pinaki Sharma, you know
Yeah.
the equation, right?
yeah,
Not used it recently, so no, so.
See, in a motor, this is in a motor, power is equal to the relation between power and torque in a motor. P power is equal to 2 pi nt. Okay, that is a motor
Okay, sir.
equation. Okay, Mr. Gaurav, you know this equation?
No, sir.
Mr. Naveen?
No, sir.
Mr. Naveen, you should know. You are actually doing design. Mr. Krishna Kumar?
Yes, sir. So, see this formula, but not regularly we are using in our.
Not, you are
design.
correct. You are not regularly using, I agree. Mr. Loganathan, sir.
Sorry, sir, I think I'm not used this formula.
Okay. Basically, this equation, let me tell you all of you, this is not a new equation. This is your BE engineering equation. And I also was not using this equation earlier because when I joined our company like ABB, TC or all these companies, I'm only designing our power plant or oil and gas facility or industry. I'm doing cable sizing, I'm doing switchgear, bus bar, all those things. But I'm never using this equation in any company. Okay. But later on, when I started doing relay coordination also, I was not using this equation. But one time when I did a coordination of a Siemens motor, which was like 1.5 megawatt, something, that time I saw this equation. And then I realized that this equation is what I had learned in my engineering in the college. Okay. Power is equal to 2 pi n is the speed, t is the torque. So you have your power.
Sir, here
Yes, sir.
denominator any 60 something will come, sir. I remember.
Yes, sir. That is actually when you take your speed, they will convert it to RPS, rotation per second.
Oh, okay.
You try now, take 132 kilowatt, divide it by 2 by, you take 132 kilowatt. Let us try this. Take it to, you do it in Excel, 2 pi, and take the speed 1500 RPM. It is in arc rotation per minute. Make is rotation per second and t. Determine the torque. Let us see. Okay. Can you check in the Excel and tell me 132 kilowatt divided by 2 star by star 0.
840 Newton per meter?
Sir, 840, yeah?
Yes, sir.
Okay. Okay. Okay, sir. Just go. Back to this one. So here you can see the nominal torque is given as 1270.
Sir, here the motor RPM is also not 1500 actually.
What is the RPM, sir?
I believe 1000 or something, 992.
Yes, sir. Where? Okay. Okay. Thank you for the observations. Very good. Please check with this RPM. Please check with this 992 RPM. What is the torque coming? T is equal to P divided by 2 pi n. How much, Pinaki?
Yes, sir, 1 second, sir. So this is 132 divided by,
And here the frequency is also 50 hertz. So
yeah,
that
then you get 1271, sir. Then you get 1271 Newton meter.
How much you are getting?
1271.
Okay. Yes, Mr. Gaurav, what is your doubt?
and then in this data sheet frequency also is 50 hertz. We have used 60. We were using 60 actually.
We have not used frequency.
No, sir. Here 2 by 80. I am n is not that 60 is not 60 hertz, sir. That n is 60 seconds.
Okay.
Second.
Okay, sir.
Because RPM was given in RPM, rotation per minute, I converted to RPS. Okay. So now here, so this torque is very important. So now this nominal torque, no? Now starting torque, you see, he is given how much? This is the starting torque. It is 3.7 times. So when you multiply by this, you will get the starting torque. Now at 80% voltage, the torque will be how much? V square. It will be how much? 0.60. It becomes 60%. Okay.
64 times, 0.64 times.
Yeah. So like that, you can determine the new torque. And next class, I will tell you why I did this. Okay. I will explain you about the next class. Okay, today I think we are.
So the previous curve, the previous sheet of this presentation, can you just go to the previous sheet?
Yeah, please tell me.
So that curve on the left side, could you just speak on that? We didn't. I don't think we covered this one. The graph on the left side.
See, this is same. This one only. This is there is no difference. Okay, this is almost same. Starting current and
Okay.
this one the same. Why I didn't explain was it was similar because there is no much difference. That is
But what is that high inertia load and that acceleration thermal limit? Something, there are two extra elements in that, no? What is that, sir?
high inertia motor is telling actually he has taken one example of a particular motor. This is curve. See, when the motor inertia increases, what happens? Starting time increases. Okay. Motor inertia,
Okay.
the relation between inertia and starting current, I will explain in the next class. Okay, inertia is just like a weight. In linear system, we have kg weight. In the rotational system, we have our this one. See, inertia is there in linear system also, rotational system also. Linear system, I have normal inertia, and rotational, I have angular inertia. And that inertia is very important because it tells about the starting time. In the next class, I'll explain you about that inertia thing. Okay. Okay, Mr. Pinaki.
Yes, sir. Fine, sir.
Because see, I'm trying to explain one by one slowly. I don't want to mix up, mess up, and make a high load. Is it clear?
Yes, sir.
Any doubts on today's session, sir?
So can you go back to the previous slide? I mean, just my only one doubt is there.
Yes, sir.
So previous slide to this. So next, this one only. So this accelerating thermal limits, that upper part, that locked rotor thermal limit, that is the curve at which the locked rotor will come into kick. I mean, can you just speak on that? The accelerating thermal limits.
See, this is the running. You can start like
Okay.
this also. See, when I start, this is my starting. At the time of starting, you are fully standstill, right?
Yeah,
What is your RPM when you are starting?
0,
0. Okay. What is the RPM when you are running?
1500 or whatever the rated speed.
Okay. 0 to 1500, what do you call it?
Range.
Oh no, when you are 0 to 1500, when you are shifting from 0 to 1500, how do you increase? Do you go to 1500?
Acceleration.
So this is the acceleration. In other words, this is starting, this is accelerating, this is running. Okay. You see
Okay.
the cycle of a motor. It starts here, it goes like this, it reaches here. Okay. So this curve is basically the acceleration. During acceleration also, see lock rotor thermal limit, I'll tell you what it is. I have a motor, okay? My motor has jammed. And my motor has to start in, let's say, 20 seconds. In 20 seconds, if my motor does not start and the motor is jammed, 25 seconds, if the jam continues, my motor will burn out. Okay? That is, all those points are given by this curve. And now my motor is no longer jammed, it is running, it is accelerating from 0 to 1500 RPM or 900 RPM, whatever it is running. Okay, my motor is accelerating, but when it is accelerating, it is taking some time. Now you see, when my motor accelerates, the time the starting current has come down from, let us say, 6 times to 4.8 times, 4.5 times. If that time increases this value, then also my motor will burn out. So that is what this curve will tell. Okay, clear?
Can you repeat it once again, this last point?
See this thing, this particular thing right now, again, when I plot the Excel, I will tell you. Okay.
Okay.
Because today already I have told a lot. I don't want to confuse you. So some of these things, whatever I told now, if you have not understood, no problem. Again, I will tell you when I'm doing the Excel. Once again, I will tell you. So this one, see, this one is this line represents the lock rotor limit. That is when the motor is got jammed. This line represents the running. When the motor is running, if it gets overloaded, there is a rise in temperature. How long can I allow that overload? That one, this curve will tell. Now this line is basically the acceleration thermal limit. Means when my motor is, this is standstill, okay? The motor is not rotating. From standstill, my motor starts accelerating from 0 to 900 or 0 to 1500. That time also, if the acceleration takes more time, or during acceleration, if there is no proper heat dissipation, or during acceleration, if it's drawing more current, whatever it is, and if it gets overheated, that time what happened, this is the thermal limit. If my motor is accelerating and it is at 4.8 times current, and if it increases 30 seconds, let's say it go to 35 seconds, my motor will burn out. Okay, clear?
Sir, one doubt here, sir.
Yes, sir.
In whenever motor curves, I have seen this cold and hot thermal limit curves. Sir.
Yes, sir.
So which one we need to plot, sir? Hot only we need to plot.
This is nice question, sir. Cold and hot thermal limit curve. You have those curve, you share with me. Let us have a look. But I will tell you, when we do our study in the software, it will add all this curve, cold and hot curve. Okay. And when we do this, when now in our Excel, we can't add our hot curve. We are adding only cold curve. Why I will tell you. When we go for hot condition, what happens? I think at that time I had drawn this. Able to see the screen? Able to see the
Yes, sir.
screen? See here,
Yes, sir.
this is cold condition. I'm starting here. If my motor was hot, I would have started here and I would have gone here. So my temperature rise would have been more, and my temperature is more. Naturally, what happens in this curve? This curve, I will reach it very quickly. Okay. So there will be a change in the curve also. But I can't plot hot curve here. That is the limitation of my Excel. Okay.
So, sir, in dynamic only we can plot this hot curve correctly, or in software hot and cold, if you are putting, that will come correctly. Or for hot condition, we need dynamic modeling, sir, in software.
Actually, the relay coordination, we are not using any dynamic modeling at all, sir.
Okay, so this cold is enough.
Yeah. So
Okay.
for today, I will end the class. Okay. So any doubts is there, you can post in the WhatsApp group. I have tried to be very interactive and answer then and there. Still any doubts are there, we can post in the group and we will take it up tomorrow also. Okay.
Sir, I posted one message in the WhatsApp group last week that SKM tool, it shows transformer. There are two curves for the windings, one for the primary and one for the secondary.
Yeah.
Does that mean? Yeah, but when we are giving the protection, we give it only for the primary winding, right, sir?
No, I think last time I explained you this one, so the transformer damage curve. This one, I am taking the overall damage curve, what I'm doing in the, I saw your question last time, the SKM. When I say the damage curve, I'm talking about the complete damage curve of the transformer, right?
No, but when you say complete damage curve, I mean, we are looking at primary winding. So protect the primary winding because the HT breaker will be on the primary side, right, sir?
You're right, the breaker is on the primary. The breaker, primary breaker will open, it will stop the current to both of them. So when I said damage, I'm talking about the damage of the full transformer because the heat is stored where? In the oil, right?
Yes, sir.
Does the oil differentiate between primary and secondary?
It does not, but then what happens is I'm not understanding, sir. I mean,
See,
we will
heat generated.
curve.
I think this, I will explain you this concept next class, okay?
Okay, sir, fine, sir.
I will write down.
Okay, sir.
And I will explain. Okay, sir.
Okay, sir.
Excuse me, sir. So
Yes,
for
sir.
transformer damage curve, for the transformer protection, we usually use temperature rise limit. For say for 40-degree ambient temperature, we allow to rise the winding temperature